This number, the sum of squared model, in other words, the difference between the total sum of squares and the sum of squared residuals, is equal to 10.88. That's not a number that we see in the sum of squares column of the ANOVA table. However, it's equal to the sum of the sum of squares due to VOR and the sum of squares due to log weight. In other words, these three numbers here do add up to the sum of squares total, so sum of squared total minus sum of squared residual gives us sum of squared model, which is then in this ANOVA table being further decomposed into the part of the sum of squares due to the model that's because of VOR, and the part of the sum of squares due to the model that's due to log weight. So this is just about 9, this is just about 2, this is just about 11. Those numbers add up. Now I'm going to run the equivalent regression. So I'm calling it M3 because it's the same model. It's the third model we're running, but we're going to call it .lm because we're going to use the lm function to predict log sleep based on VOR and log weight. So I'm summarizing that. And what we see here is the conventional regression output. We have estimates for the coefficients of the model we've specified. So that means we have an estimate of the intercept. We have an estimate for the coefficients for 4 of the 5 possible values of VOR, and there's 4 or 5 of them because one of them is the baseline. And then we have an estimate of the coefficient for log weight. These are coefficients that are being estimated regardless of whether I use the function LM or AOV, but the default for the ANOVA, the AOV function, is to show you the ANOVA table, and the test for whether each of those predictors separately is important. And the default for the LM, for the regression, is to show you the estimate of each of the coefficients along with a p-value that's specific to each of the coefficients. So I want to compare these. I want you to see how these compare. So to make them show up on the same screen, let me run again the ANOVA output here. And I want to compare this row of the ANOVA table, which is an f-test for whether log weight is an important predictor, whether it's a significant predictor, and this right here, which is a t-test for whether log weight is a significant predictor. These are exactly the same test. Note that the p-values are the same. They're essentially 0, but to be very specific, 5.17 times 10 to the negative 11. For any practical purposes, that's 0, but the point we're making here is the numbers are the same. And the t statistic is the square root of the f statistic. So if I were to take negative 7.633 and square it, I get 58.26. That's exactly the f statistic that's shown here. These are exactly the same test. Both the test summarized in this row of the ANOVA table and this test summarized in this row of the regression output are comparing the actual model that we specified to the same model if we'd left out log weight. In other words, it's comparing the model with both VOR and log weight to the model that has VOR only. The null hypothesis is that the model with VOR only is sufficient. So we see the equivalent tests shown in the ANOVA and regression outputs for log of weight. But for VOR, that's not true. For VOR, which is a categorical variable, a categorical predictor, the ANOVA table is doing a test for whether VOR matters at all. So let's start with the null hypothesis that we don't need VOR in the model at all. And that's what this p-value 0.02 is showing. That VOR is, we have a significant p-value, so VOR does seem to matter overall. We're testing the null hypothesis that VOR is not needed. But that particular p-value does not appear in the output of the regression because that question is not being asked as part of the conventional regression output. We're fitting the same model, but we're not asking the same question. Instead, the p-values that are shown here are testing whether each particular dummy variable, indicator variable for a particular level of VOR is necessary. So for example, this row here is a summary of a t-test for the null hypothesis that the coefficient for VOR being missing isn't necessary. In other words, if we left out the indicator for VOR being missing, but kept the indicator for VOR being herbivore, or for the animal being an insectivore, or for the animal being an omnivore, if we kept these predictors in here and just omitted this one, would our data be surprising? That's different than the test for whether VOR matters at all. This is a test for whether one particular level of VOR needs to have its a coefficient other than 0 in the model. So it's the same model, but the tests that are being shown, the questions that are being asked are different. So this is relevant because you need to be sure that you ask the right, that you look at a test that is related to the question that you're actually trying to answer for your research project. If your research project is about whether a particular variable matters at all, any of the levels of it, then you're more interested in the output that is conventionally shown as part of the Anova. You're interested in f-test for whether var matters at all. Whereas, if you're trying to come up with a model that might include some of the different possible categories of var, but not all of them, then you want to be looking at t-tests for whether each particular category of var needs to have its own term in the model, or whether you can omit some of the terms but not all of the terms of var. You can also see that the f-test shown at the bottom of the regression output is no longer an f-test that's also shown in the Anova table. When we had only one predictor, this f-test that was at the bottom of the regression was identical to the one f-test that was shown in the Anova table. But now our Anova table has two different f-tests. It has two p-values in it, and neither one of them is identical to this f-test. So again, this is a case, an example of the two different default sets of output just asking different questions about the same model. So this f-test that I've highlighted here at the bottom of the regression output is doing the same thing that the f-test at the bottom of the regression output will always do. It's comparing the model we specified to the equal means model. So the null hypothesis is that the equal means model is sufficient, none of these predictors are needed, and then the p-value tells us how surprised we are by this data set if actually the truth is that we have an equal means model. And so what we're seeing here is we can definitely reject the null hypothesis that the equal means model is sufficient in favor of a model that includes the predictors that we've included here. That test is not part of the Anova output we have here. Here we have a p-value for whether var is important, and we have a p-value for whether log weight is important, but there's no p-value for whether var and log weight as a whole are an appropriate alternative to the equal means model. Remember that when we derived f-tests, we talked about comparing different pairs of models and calculating the sum of squared residuals from two different models in order to get to the f-statistic. That's what's going on here. Every p-value you see in either of these sets of output is comparing two models. Again, this f-test is comparing the equal means model to the model we specified. This p-value for log weight here or here is comparing the model we specified to the same model, just omitting log weight, etc. For any of these p-values, we can determine what the two models are that are being compared in order to generate the p-value. If we were to create the residual versus fitted value plot using the regression, we get exactly the same plot that we had using the Anova, because it's exactly the same model. We continue to see this model doesn't actually fit very well. Just as before, we can try to confirm the residual standard error. We can try to confirm the values that are shown in the bottom of the regression output. Remember, we calculated a moment ago this SSR3 based on the residuals from the Anova, but since those are identical to the residuals that we get from the LM output, we can use them here. If I take the sum of squared residual and divide by the degrees of freedom associated with the sum of squared residual, so that's 77, and take the square root, that's 0.3928. That's exactly the residual standard error, because that is by definition the residual standard error. So remember, we use the residuals to confirm this number. What we're saying now is this number divided by this number, which by the way is equal to exactly this number, is just the residual standard error squared. The mean square error is the residual standard error squared. So these are just different ways of showing the same thing. This row here is showing the same information as this row here. We can also confirm R squared. Even though the Anova table breaks down the sum of squares due to the model into the sum of squares that's due to var and the sum of squares that's due to log weight, R squared is still defined as the total sum of squares due to the model divided by the total sum of squares overall. So there's our 0.4781, that's right here. And similarly, we can confirm that adjusted R squared of 0.4442 if we run the appropriate function of the sums of squares. And just to make sure that you see it repeatedly, if we look at the fitted values that are generated by each of our sets of model output, those are the same numbers. right? So we see across each row the two fitted values are the same from the two models. That's exactly the same thing that we're doing in both cases. The only reason that we even have two separate functions, LM and AOV, is that in particular cases you might be interested in the questions that are answered by default as part of the regression output, or the questions that are answered by default as part of the Anova output. Next, I want to illustrate the importance of properly determining whether a variable you're trying to use as a predictor is supposed to be categorical or continuous. You will be inappropriately interpreting your results if you get it wrong in either direction. So in order to show that it's inappropriate to take a continuous variable and handle it as categorical, I'm going to focus on a variable we haven't focused on too much yet in this discussion. So this is the REM sleep variable, and I'll summarize it here. You can see that it's NA for 22 of the animals in this data set. So we're gonna allow some rows to drop as we go through this small part of the tutorial. That's fine. Those 22 rows will drop out, and I don't have any compelling reason to deal with that here because we're not trying to actually interpret these models. We're just trying to illustrate how regression and ANOVA relate. So okay, you can see this is a continuous variable, right? You can take the mean of it, etc. We can make a box plot of REM sleep, and we can see that it has a particular distribution. Nothing shocking here. Make a plot where the x-axis will be REM sleep and the y-axis will be log sleep. You can see that perhaps we should think about logging REM sleep. I'm not going to bother here because I'm not trying to actually fit this model, but certainly there's a relationship between the amount of REM sleep and the total amount of sleep, which should not be something that's shocking. Okay, so I am going to run a regression of log sleep on REM sleep, and I'm going to run the Anova as well. These are both the same models, but I want to show you both the regression and Anova output. Remember that REM sleep is a continuous variable. Okay, so here's the output from the linear model. I've got estimates of my coefficients. So if I fit a line to this pattern that I see here, even though a line might not be appropriate, if I were to fit a line, its intercept would be 1.7 and its slope would be about 0.3, and we have tests for whether each of those is significantly different than 0. They both do appear to be significant, which makes sense. And we have the usual things, and it's nice that we have a reminder that observations are deleted. That's good to see. We have a residual standard error, we have our multiplier squared, we have our f-statistic, and then if we look at the Anova output, this is exactly parallel to the example that we talked about before when we used just one continuous predictor of log weight. Because REM is continuous, degrees of freedom is equal to 1, so that's a place to check that we really are dealing with this as a continuous variable. We'd have that 1 there. This p-value here is identical to this p-value here because they're the same test, and you see the p-value again here. This is also the same test. So again, this is exactly the same thing that we illustrated earlier when we had just one continuous predictor. What happens if either accidentally or because I'm confused, I handle this as a factor? So in other words, I think that each possible value of REM sleep is actually a different categorical level. So if I make a box plot of log sleep by all the different possible values of REM sleep, so I make this a factor variable, I can see the same pattern that I saw before. And in fact, I like this kind of plot because this is how I like to think about regression. For each value of the predictor, what's the distribution of the outcome variable? So this is what we see here. But what if we incorrectly use this predictor as a categorical predictor? We're not going to be taking into account the fact that as REM sleep increases, there's some particular way that log of sleep increases. Rather, we're going to be thinking about each of these box plots as a separate entity with no particular ordering to them. So if I run the linear model and also the Anova, because it's the same model, just with different default output of log sleep on the factor version of REM sleep, I should be able to tell immediately that something went wrong. So it's important that you know how to identify a situation like this. Looking at the regression output, what we see happened is that because REM sleep was handled as a categorical variable, we have coefficients for all but one of the different possible values of REM sleep. So this row here gives us the coefficient for the indicator that REM sleep is equal to 0.4. This right here is a coefficient for the indicator that REM sleep is equal to 0.5, a coefficient for the indicator that it's equal to 0.6, etc. So now for every value of REM sleep that occurred in the data set, except for one baseline value, I have a different coefficient that I'm estimating. So there are occasions when this could be something you wanted, like maybe you had a categorical variable with lots of categories. For example, maybe it's different states in the US. But most often, if you see something like this, lots of different possible coefficients being estimated for a particular variable, perhaps that wasn't really supposed to be a factor variable. Perhaps it should be a number and you're not handling it as a numeric. Similarly, when you look at the Anova output, what you see here is that the degrees of freedom are something very different than 1. So there must have been 32 different possible values of REM sleep. So the degrees of freedom here is equal to 32 minus 1 is 31. This is the place to check. If you are trying to make sure that the variable you have, if it's supposed to be continuous, really is being handled as continuous in the linear model that you're running. If you're looking at the Anova output from that linear model, the degrees of freedom should be 1 here if it's handled as continuous, and here that's not the case. So avoid that. Make sure that if you have a continuous variable, you actually handle it as continuous. But the problem also goes the other way. If you have a categorical variable, it's a mistake to handle it as continuous. I think this is a more common error. You'll often have a variable in a data set that's categorical, but the values are labeled 1, 2, and 3. And if you read those in as numeric, R is going to assume that's a numeric variable as opposed to a categorical. So to show you what could happen here, I'm going to create something called vor as num, which is going to be a numeric version of the vor variable. So remember that the vor variable is categorical. So if I do this, I can make a table. So instead of now labeling carnivores, herbivores, omnivores, etc., I'm just calling the same categories 1, 2, 3, 4, 5. I can summarize this now. Now here's where you can tell that this numeric version of vor is different than the factor version. You can't take the mean of omnivore, carnivore, etc. But if I start using the labels 1, 2, 3, 4, 5, now I can take the mean. And that's not good here because these are arbitrary labels 1, 2, 3, 4, 5. I could have called them 5, 4, 3, 2, 1 and it would be just as meaningful. So these numbers don't mean anything, the max, min, the median, the mean, and yet it's possible to calculate them if I haven't turned this variable into a factor. Right, so if I summarize the original vor variable, this is what it should look like. It's a categorical variable. It doesn't make sense to take the average of labels that I might put in these numbers. We can just do a check that we did this correctly. In other words, we do indeed have 5 different numbers that correspond to the 5 different possible labels. So what happens if this variable is handled as numeric, even though it should be a categorical variable? I'm going to show you both the regression output and the Anova output. Okay, so what we see here is even though we know this is a categorical variable, when you look at the regression output, you're only seeing one coefficient. You're seeing a coefficient for the slope of a line where the x-axis is equal to these numbers 1, 2, 3, 4, 5. And that's not appropriate here. What I would rather see, what's appropriate to see, is separate coefficients for all but one of the different possible levels of the vor variable. Similarly, when I look at the Anova output, I can see the degrees of freedom is equal to 1. What I expected to see was 5 minus 1 is 4. So this degrees of freedom for a particular predictor is often a really good place to check that a variable is being handled as numeric or categorical appropriately. I want to show you that if I make a plot where the x-axis is this numeric variable of vor and the y-axis is log sleep, right? These are the labels 1, 2, 3, 4, 5. And then if I put on the line that results from incorrectly running this regression with vor as a numeric variable, it does indeed draw a line. R doesn't know what your context is. It doesn't know this is really a silly thing to do when this means carnivore, this means herbivore, this means omnivore, etc. R doesn't know this is ridiculous, so it'll draw the line anyway, but the slope of this line has nothing to do with any sort of research question that you might be asking. If the variable is actually categorical, you need to make it into a factor before you put it in either your Anova or your regression, or else the results aren't going to make sense. I'm now going to take an opportunity to talk about something related, a little bit different, but important, and we'll use that to get back to some important things to say about the way Anova output is displayed by default in R. So we're going to run a model that may not make too much sense, but we're doing it for a reason. We're now going to think of body weight as the outcome variable, so we're trying to predict the animal's body weight. And we're going to do that with a couple different possible predictors. We're going to consider sleep total, now not logged, and I'm doing that to make things work a particular way. So I'm going to try to predict body weight based on the total amount of sleep each animal got, and I'm also going to consider as a predictor the amount of time when the animal was awake. Now, importantly, these two variables, awake and sleep total, are very related to each other because there's only so many hours in a day. Specifically, there are 24 hours, and if you're asleep a certain amount of the day, then you're awake the rest of the day. If you don't sleep a lot, you're awake a lot. If you sleep a lot, then you're going to be awake very little. So there's definitely a correlation between these two, which we'll look at in a moment. So I'm just going to summarize these models so you can see them. If I run the model predicting body weight using the number of hours awake and I summarize it, here we go. You can see that the coefficient for awake is significant. In other words, it appears that including awake, the number of hours awake as a predictor for body weight, gives us much smaller residuals than just using the equal means model. Awake does seem to be a significant, useful predictor of body weight. Similarly, if I look at the model predicting body weight using only sleep total, it's very similar. I can see that using sleep total alone is a significant predictor. Sleep total leads to a better prediction of body weight than the equal means model does. What if I put them both in? Here's what we're trying to illustrate. When I put them both in, sleep total and awake, even though I saw that each of these predictors, when used as the only predictor in the model, did lead to significance, now these are not significant at all. And also some weird things are going on here. Look at these ridiculous coefficients. There's some strange things going on, and these p-values are now really large. So what's happening here? Importantly, let's note this f-test at the very bottom. Remember what the f-test at the bottom of the regression output does. It compares the model you ran to the equal means model. And the null hypothesis is always the reduced or simpler of the models you're comparing. So the null hypothesis is that the equal means model is sufficient. This p-value is telling us that if the truth is that the equal means model is sufficient, then this data would be really surprising, right? This p-value is really small. In other words, the model that includes both sleep total and awake is much better than a model that includes neither sleep total nor awake, even though neither of these variables is significant when you put them both in the model. So what's going on? This is called multicollinearity. The idea of multicollinearity is that one way to think about it is just that the p-values associated with any particular variable will change depending on what else you put in the model. But more specifically, what we're doing here is reminding ourselves of what the t-tests that are shown as part of regression output are actually doing. Each test compares the model you ran to the same model without that predictor. So this row I've highlighted here summarizes a t-test that compares the model that includes both sleep total and awake to the model that only includes awake. And what we're seeing is if awake is already in the model, we don't also need sleep total. This row is summarizing the results of a t-test that compare the model that includes both sleep total and awake to the model that only includes sleep total. And we're seeing that if sleep total is in the model, we don't also need awake. But neither one of the tests shown in these rows is reflecting a model that excludes both sleep total and awake. Both of these are tests for what would happen when you have one of these predictors as opposed to both. This test here is looking at whether it's important to have some information about how much time you spend asleep and awake as opposed to none. And we know from looking at the previous models that knowing how long you're awake tells us a lot about your body weight. Knowing how much time you sleep tells us a lot about your body weight, right? And knowing both how much time you spend awake and how much time you sleep is important for learning about your body weight. The tests that you see as part of the regression output are not telling you overall whether the predictor is important, only whether this particular model would still be appropriate if that one predictor were dropped. So it would be a mistake in general when you're fitting models to run a regression with lots of predictors and then just omit all the predictors that don't look significant, because those could be the most important predictors and you just can't see that because of the other predictors that you've included in the model. When does this sort of problem occur, this multicollinearity issue? This occurs when the variables that you're using are highly correlated with each other, when the predictors are highly correlated. So I'm going to make a correlation table of these three variables: body weight, sleep total, and awake. So each of the cells in this table is showing me the correlation between two of the variables, and I just have a 1 when it's the same variable compared to itself. So what we see is that the correlation between sleep total and body weight is negative 0.31, and the correlation between body weight and awake is positive 0.31. And crucially, the correlation between awake and sleep total is essentially negative 1, which makes sense because the more you're awake, the less you're asleep, and those two numbers have to add up to 24. So these two numbers are highly correlated, which is why putting either one of them in the model gives us a lot of predictive power about body weight, but if one of them is already in the model, we don't also need the other one. I can see this by plotting as well. It's a nice way to plot multiple variables at the same time. So this is a plot of each of the variables against the others. So for example, this is a plot where the x-axis is sleep total and the y-axis is body weight. This is a plot where the x-axis is awake and the y-axis is body weight. And one thing to note here is that when the x-axis is awake and the y-axis is sleep total, they're perfectly correlated in this particular data set, and that's why I chose these variables to show you. This will happen to a lesser extent if there's less of a correlation here, but if the predictors are correlated with each other at all, this general idea will apply, that the p-value shown in the regression output when you include multiple predictors does not tell you whether a particular predictor is related to the outcome, only whether it's needed in the model when all those other predictors are already there. Now let's look at the same output for the ANOVA. So I can show you a summary of the ANOVA table that looks at body weight regressed only on awake. And I can see that I appropriately handled awake as a continuous variable because I have a 1 here. And this p-value of 0.409 is exactly the same as the p-value I got when I ran the regression, because it is just the regression of body weight on awake. And this f statistic is the square of the t statistic that we had earlier when we ran the model predicting body weight only on awake. Similarly, I can run the model of body weight on sleep total, and all the things I just said about awake are true here for sleep total, comparing this to the model that we got from LM of body weight on sleep total. Now I'm going to regress body weight on sleep total and awake using the ANOVA. And this is where things are going to get a little strange. So I want to look at the results that we have here, and I want to compare them to the results of the regression that included both terms. This is the results of the ANOVA that includes both terms. I want to look at the results of the regression that included both terms. So that was this. Okay. So remember, when we looked at the results of the regression that included both terms, neither term was significant. But when I look at the results of the ANOVA that includes both terms, one of them is significant. So what's going on here? What you're seeing here is something kind of unusual about the way R chooses to ask questions about an ANOVA with multiple predictors. So this row here, this bottom row, is actually identical to this one here. These are the same test. So this t statistic squared is equal to this value. This p-value is exactly the same as this p-value. We just have a little bit of rounding. Both this row and this row, in other words, the row corresponding to awake both in the ANOVA table and in the regression output, correspond to a test comparing the model that has only sleep total to the model that has both sleep total and awake. Both of those are doing that, so that's exactly the same test. The question is, what's going on with this p-value? Why is it so different? Why is this row of the ANOVA table associated with sleep total so different from the row of the ANOVA table associated, the row of the regression output associated with sleep total? And the answer is that when you run an ANOVA on multiple predictors, what R does is it thinks about these predictors sequentially. So this first row of the ANOVA table is not a test comparing the model with both predictors to the model with only awake. Rather, it's ignoring awake altogether, and this row right here is comparing the equal means model to the model with only sleep total.